Okay, now we know what gradient descent is. We're gonna look at ways to improve gradient descent. Yeah? So make gradient descent better. How can we do that? What does it mean, make it better? It means we allow it to converge faster. We survive local minima. Yeah? And we avoid to overshoot. Because once you overshoot, you know, you have to come back. Yeah? So let us first take a look at some intuition here. So here we have, remember, on the vertical axis your cost function, on the horizontal axis you have your feature W. Yeah? In this case, yeah, you want your learning rate alpha to be relatively small, yeah, because the curvature is quite big. Yeah? So you don't want your alpha to be too big to avoid oscillations. Now in this case it's different. This can be again a cost function and another weight, yeah, of another feature. Here you want your alpha to be a bit larger because it will make you converge faster. Okay? So what do we learn? Ideally we have a different learning rate for each feature. And also what we want is we want alpha to be smaller as we come closer to the minimum. So what you see here is that curvature plays an important role. Curvature plays an important role. And if we say curvature in mathematics, we mean the Hessian. The Hessian matrix. The Hessian matrix gives us information about curvature. Okay, let's take a look at Newton's method. Newton's method is a second order optimization. And remember, we just calculated or determined the Taylor series of C of W plus delta W. But we stopped here with the first order term. We don't have to. We can actually add a second order term. So the second order term would be the Hessian of C, and the Hessian of C in the point W, yeah, times delta W squared divided by 2 faculty. This is nothing more than just adding a second order term to the Taylor series. Let's take a look at Newton's method, what it actually means. So what we're going to derive first is Newton's way to find the root. It has nothing to do with machine learning or with finding a minimum, but we're going to use the analogy in order to go from this point to where we actually want to be, which is a second order optimization. So typically, to find the root, yeah, you start in a certain point. And let's call this point W0 again, yeah. And then we take the tangent line, and that tangent line, you know, ends in a point W1, yeah. Now, so let's call this angle theta here. Yeah, we know that the tangent of theta equals this piece. This vertical piece here, and this is basically the cost in W0, yeah, equals cost in W0 divided by this piece, and that's W0 minus W1. Yeah, that's very simple trigonometry. Now the tangent line, we've seen that that's exactly the definition of a derivative. So that means that tangent of theta is the same as the derivative of C with respect to W, yeah? And that is equal to C prime W. And we take it in the point W0. Okay, so what we're going to do now is bring this one in there. So that means that we have that C prime in W equals C in W divided by W0 minus W1. This is simple algebra. I replace this one by this one. Okay, so that means that C prime W times W0 minus W1 equals C of W. Okay, now we're gonna of course work this out. So that means that C prime in W times W minus C prime in W0 times W1 equals C in W0. So that means that C prime W0 times W0, and this I'm going to bring to the other side, equals CW0 plus, okay, so that means that if we isolate W1 here, we have C prime W0 times W0 minus C in W0, and I divide it by C prime in W0. C prime in W0. Okay, so that means that W1 equals, so these two cancel each other, so W1 is W0 minus C in W0 divided by C prime in W0. Yeah, that's gonna be your next iteration, W1, and you continue. Yeah, we will not go to the end and find the root. We will just use this equation to deliver an analogy in terms of second order optimization. Okay, so we have W1 equals W0 minus CW0 divided by C prime in W0. That's exactly the formula we have. Now instead of having CW here, we could change that and we could place C prime of W here. Okay? So CW becomes C prime W, and the derivative then becomes double prime. Yeah? So, as by analogy, W1 equals W0 minus, and C of W now becomes C prime of W0, and prime becomes double prime. C double prime in W0. So that's how, by analogy, we find the second order optimization technique, and this is called Newton's method. This is called Newton's method. What does this tell us? Well, first of all, you have here the Hessian. The double prime means the Hessian. And not only does it mean the Hessian, it also means the inverse of the Hessian. So don't underestimate this computationally. It's quite tough to calculate. Just to show you a little bit more of intuition, well, instead of finding the first order derivative in this point, when we change it to C prime, That means that in that point we approximate it by C double prime in the point 0. And the new point is the minimum of that curve. Yeah? That's then the new point. That's your W1.